Yeah, so what it means, gait variability, meaning, when a healthy patient or healthy person is walking, the length between our left and right step, if, as long as we're not, trying to avoid some obstacle, is relatively same. And the timing of when we do the left and right step, right, it's a continuous cyclical movement, and it's pretty much same all the time. Doesn't vary a whole lot unless we want it to. But in Parkinson's patients, that when they walk, it takes more intention. And what they you often see is that the timing between the left and right step is different, and the variability is high, and the step length may be different. So by restoring symmetry, you can think of it as, potentially restoring some stability in the walking, so that, they're kind of getting back in the cyclical movement and just having more stable base of support as they're walking and shifting their center of balance. And that's one potential reason we think the patients that went through our long-term testing at home did report decreased number of falls with this adaptive stimulation. Now, in terms of longer term, months or to years, what it means, hard to say, but I'm proud to say, a couple of the patients who did the long-term study actually remained in the adaptive setting of their own volition after they were unblinded for 6 months, and one patient has been on it for over a year now. And, if we had to temporarily switch them back to the old clinical setting, the continuous traditional DBS, they reported many more freezes, falls, and their gait function, drastically deteriorated. So we know that this dynamic adaptive DBS is doing something, and this for selected patients, it may carry, long-term benefits. Yeah, so great question. I feel like heart pacemaker is something most people can understand, right? If your heart gets in an abnormal rhythm, it responds by shocking it or, pacing it in the right rhythm. Of course, that's a lot more simplistic than what's happening in the brain. Brain, instead of just a regular rhythm, think of that multiplied by a billion different neurons, and different dynamic state that's active at all times. So what we're trying to do, again, it's, delivering stimulation, hopefully eventually to the right part of the brain, the neural circuit, when the brain actually needs it. And then what we're hoping to do, right, is again like responding dynamically to what the brain needs at the time. And a few other things that's really different is, with brain stimulation, we have a lot more parameters and variables to control besides just the amplitude, the rate. We can control the pulse width, different areas of the brain we're stimulating. So if we can really fine-tune all the different parameters, we can hopefully respond to this more complex system a little bit better. Yeah, so I think one key thing and limitation is availability of the device to perform the functions we need. So, one really cool thing about this is all the adaptive fancy biomarker detection and, implementing this really sub-second rapid changes in stimulation across two hemispheres is all done by the pulse generator, meaning the DBS battery itself. So all the programming, everything is done and fully embedded. So we don't need external computers, like the BCI Neuralink system, to control this device. So, what we had access to is a research level device, investigational device made by Medtronic. So they kind of gave us the unlock, the ability to program our biomarkers, weigh them into the algorithm within the limits of the machine. Right now, first of all, the commercial devices made by Medtronic that has the sensing closed loop function don't necessarily have these features unlocked. So I think that's number one, being able to access these features and these devices for at least research purposes in the beginning. So we can try to replicate some of the findings on a larger scale. So that's number one. And number two, I think, selecting having multi-institutional, multi-center study, larger randomized study, so we can have more power, meaning more patient selection, knowing truly what type of patients actually benefit from this method of adaptive stimulation. What type of gait symptoms in itself, right? Even when somebody has a disordered gait, it can manifest as asymmetry, variability. Some people have freezing of gait. That's a whole nother, beast and symptom that we're trying to tackle. But trying to figure out specifically with this mode of stimulation, what these gait specific symptoms that respond best would be really useful. And then thirdly, I think, finding a more automated way to detect these biomarkers. As you can see by the authors on this study, took our lab, the talented group of researchers, over 3, 4 years to figure out the biomarkers. And we had to bring patients, in clinic. We had to go to their home to run these repeated trials. I think ideally, we have a device that can just sense and record brain function while someone's carrying on their daily activity. And with a wearable device, your Apple Watch or Apple phone, that can automatically synchronize what they're doing to the brain recording, and then using AI machine learning algorithm to figure out, what are the signals that correlate to the movement state. So that can really streamline this process of biomarker discovery and also the response to the stimulation testing in a more scalable fashion.